show. Okay. Any question from this time? Yeah. So today I think we'll just finish chapter 3. So it will be a bit slower. Maybe we'll finish early. So let's take a bit slow review of this time. So this time we go over this 3.4 and 3.5. So 3.4 once again is we define basis and dimension. So we say that the bases are set of vectors in your vector space that span your vector space V and they are linearly independent. And we found out that basis has a strong property in vector space. So first of all, when you fix the vector space V, then all the bases have the same number of vectors. So the number of vector n is called the dimension of your vector space. Okay. So once you fix your vector space, it has a dimension n, and every basis which satisfies those two equations will have the same number of vectors inside. And then we have this intrinsic theorem, 3.4.3, says that actually if any of the two properties, so fix the V, then any set of vectors satisfying those two properties, then they form a basis. So if your vector space has dimension n, then find n vectors that span the V, then it is a basis, and it will satisfy linear independence. And also, if you have n vectors and they are linearly independent, and they will also be a basis. Okay, so that's the basis, and so basis gives us the concept of the dimension of the vector space, and also they are very useful to describe everything inside the vector space. Then we see this concept of coordinate. We see that every vector in your vector space can be described as a unique linear combination of your basis vectors. So for example, in the standard basis, everything, so in Rn, everything can be described by a linear combination of standard basis, obviously. So we write this x1 and x2 as a vector in, say, R2. Then this is actually x1 times the first standard vector E1, and x2 times the second standard vector. Okay. And so this x1 and x2 are called the coordinate of your vector x. And we see that for every yz, we can also write x as alpha times y plus beta times z. And geometrically, if you like this, so you have your vector x, and you have two vectors that also form a basis, so they are linearly independent. And you see that x can be written as some multiple of y times plus some multiple of y plus some multiple of z. And in this example, the two coefficients are 3 and 1. And we see that, okay, and now the question is, so you get a vector in Rn, then you want to, and some basis for your Rn, and you want to find, the coefficients, the coordinate in that basis. Okay. And then we see this as a change of coordinate, actually. So because everything in Rn, we are basically expressing it as a coordinate to standard basis. So first we have this change of coordinate between standard basis and your arbitrary basis. And we find out that so there is a really simple equation to change from your arbitrary basis, the coordinate of your arbitrary basis, to standard basis. That is, you just write down the equation and you find out the standard basis element is this U matrix times your coordinate basis, coordinate in your new basis. And this U vector is just you list the the coordinate of your vectors, of your new vectors. So this U1 is 3, 2, and U2 is 1, 1. So those are column vectors, and you list those columns one by one. That's this transition matrix U. So this is the transition matrix U from your new basis back to standard basis. And then we have this algebraic matrix equation. Then we can just manipulate and see how you get C from X. So from C, how you get C vector from X vector, is just you apply U minus 1 on both sides, so it becomes C equal to U minus 1X. Okay. So you find out the transition matrix from your standard basis to your new basis is just this U minus 1 matrix. And from this, then we can then we can transform from arbitrary basis to arbitrary basis easy. And jump ahead. Okay. So if you have two bases U and V, and you want to find the transition from coordinate in V to coordinate in U, then you just transform from coordinate of V to coordinate of X by applying the V transition the V matrix. Then you apply U minus 1 to transform from X to, so go to the picture. Okay. So you go from V to standard basis by apply the V matrix. Then you go from E to standard basis to your U basis by applying U minus 1. So just do the thing between your basis and the standard basis twice. So you go from a basis to standard basis and a standard basis to another basis. Then what you do together is you apply V then U minus 1. So you do this V and the U minus 1 matrix here. Okay. So that's 3.5. Any questions so far? Not, then let's go to So we've been talking about R2, but obviously everything is similar in R3 or higher dimension. So so we have an example here, and anyway, it looks like this. And then we have this, once again, more structural results about row space and the column space. I think this will actually get more useful later, but anyway, we're talking about some property we can learn about the spaces of row and the column of a matrix. Okay. So now we study A is a n by n matrix, and obviously we can view A as rows and columns. So we have an example here. A has rows and columns, and we can view each row as a vector in this weird space of R1 by 3. Okay. And so you see A is 2 by 3, so it has two rows of 3-dimensional vectors. And so it's this first row 1 0 0 and the second row 0 1 0. And it has 3 columns of 2-dimensional vectors. So it's 1 0 and 0 1 and 0 0. Okay. So so rows can be viewed as a set of vectors, and the columns can be viewed as a set of vectors. And obviously you have set of vectors, then we can define a space span by them. So that's called a row space. And also for the columns, you have a whole bunch of vectors, then we can think about what they span. That's the column space. So it's denoted by C of A. Okay. So far it's just definition. And then we go to see whole bunch of property of row space and column space. Okay. And okay, so first property is that so we basically want to see how row space and column space transform when we do Gaussian elimination. So when you do the row operations. Okay. And so first theorem is that we see that when you do row operation on your so maybe I should it's E1. Okay. Anyway, so when you do row operation on your matrix, maybe I should just write E here. Control E. Why can't I? Okay. Oh, but it's old, so anyway, so when you do a row operation on your matrix, then the row space doesn't change. It's pretty easy to verify. You just see every operation, it really doesn't change there are 3 possible row operations, and you see that doesn't really change the span of the rows. Okay. And okay, so I think most of the property are actually about row space. Okay. Wait. Is it? Oh no, actually. Oh, it's about half. Anyway, not important. So that's the first theorem about row space. And then we define this concept of rank of a matrix. So the rank is the dimension of the row space. We define it as this here. Yeah, so you have a row space R of A, and obviously you can find the dimension of it. So it's a dimension of a row space. And then at the end of the chapter, we will see that this is actually a symmetric definition. So there is a symmetry between row and column, and this is the rank of A is actually also equal to the dimension of the column space. Yeah. And anyway, for now, we are thinking rank as the dimension of a row space. And so in our example here, we see the dimension here is 2 because you have these 2 vectors and they are linearly independent. Okay, so let's span the 2-dimensional space. And then we determine the rank of matrix. We give a way to calculate it. And once again, it's doing Gaussian elimination. So you do Gaussian elimination to turn your matrix into row echelon form. Then you just count how many non-zero rows are there. Yeah, so for example, you have a matrix here, and then you turn into reduced row echelon form. And this matrix, we call it U. And as the theorem just said, so A has the same row space as U. And U is spanned by those 2 vectors. And it's pretty easy to see that these 2 vectors are linearly independent. So to want to see that, then you go further to go to reduced row echelon form. Yeah, so maybe if U is reduced row, okay, it's a little confusing. Yeah, and you can go to reduced row echelon form to see that there are actually 2 independent vectors. So dimension is 2. And but if you just want to find the number, then you don't need to go to the whole reduced row echelon form. You just need to go to row echelon form and see there are 2 rows. Okay. And yeah, so rank of A equal to 2 because you go to row echelon form and you see there are 2 rows here. And so that's about row space. And we kind of go back and forth between rows and column. It's a bit funny, but well, I think it's okay. And I think then we go to some property about column space. And so column space tells us something about this linear system AX equal to B. Okay. And so one thing that's very obvious is that you want AX equal to B, and as we said always, AX can be seen as a linear combination of the columns of A. So AX can be written as this, and so that's x1 times the first column, and x2 plus x2 times the second column, plus all the way to xn times the nth column. So it's a linear combination of the columns, and with the coefficient being those coordinates of x. So AX equal to B satisfy means that B is a linear combination of the columns of A. And so that means B is inside the column space of A. And you can pretty see this is an if only if. So AX equal to B is consistent if only if. Yeah. if only if B is in the column space of A. Okay. So yeah. I guess here we prove only if, so we have if B inside, if A is equal to B, let's see which way. So here we have this is A is equal to B is consistent, and so here we have to prove that A is equal to B is consistent and B is inside column space. And the other way is B is an column space. Then you can find the x1 to xn, and then you can both go backward, and you see that A is equal to B has a solution. Okay. So yeah, this is about column space. It describes the solution set to A is equal to B. Okay. And so yeah, then we just write this as a theorem once again. And okay, so X will be consistent if only if B inside column space of A. Then then we start to think about yeah. So from this theorem, we can think about how many solutions it has, and that will say something about our column space. So first, let's go to this special example of B equal to 0. So we have seen that this A is equal to 0 equation actually tells us quite a bit about our matrix A. Remember from one point we start this study in chapter 1. In chapter 1, so we had this theorem 1.5.2. Okay, and but now let's go back to column space first. So we want to see what about A is equal to 0. How many solutions does it? Once again, it always says the trivial solution of X equal to 0. Okay. And from seeing this, we see that A is equal to 0, and so this equation either has one solution or many solutions. Okay. So if it only has one solution, and that means that the columns of A are linearly independent. Okay. And that's just from you write down this as a linear combination of columns, and you see that this is exactly the definition of whether it's linearly independent. So it's linearly independent if only if this equation only have the trivial solution. And so yeah, so that's A is equal to 0. We have another characterization. It's only has trivial solution if the columns of A are linearly independent. And you can compare this to our characterization in theorem 1.5.2 and together with chapter 2. Okay, so in 1.5.1.2, we were characterizing this for for the square matrix A. So when we do that, A was like n by n matrix, the square matrix, and it only has a trivial solution if only if A is typo, A is non-singular. Okay. No, this way. A is non-singular, and so the chapter 1 we have the theorem that have three conditions of A being non-singular, so X equals 0 only have non-trivial solution is one of them. And also from chapter 2 we see that square matrix A is non-singular if only if we determine not equal to 0. Okay. And okay, so by those two we see that this Ax equal to 0 only have non-trivial solution. So when A equals square, A equals 0 only has non-trivial solution if only if determinant not equal to 0. And also you see that this equivalent to this was also we also talk about in theorem 3.3.1. So we say that in there we were listing vectors. So the x1 to xn are basically okay. So it's a little confusing. So instead of A and A1 to AN, we have x1 to xn and this big X matrix. So in 3.3.1, we say that we have n vector in Rn, so x1 to xn, and they are linearly independent if only if okay, so it's not those two, sorry. Yeah. So they are linearly independent if only if the matrix you form by listing it together is non-singular. So basically we are saying, so this 3.3.1 is saying the middle condition. So we have three conditions here, and we are saying the middle one is equivalent to Wait, so it's really long. So the middle one is this non-singular, then it's linked to. So maybe I should draw here. It's linked to, it's linked to obviously those vectors are IOI, and those vectors are IOI, they are the column vector of your matrix. So we are saying theorem, yeah. So theorem 3.3.1 is linking this to this, okay. Okay, so here we have a general, once again, here we have a general description of Ax equals 0. Only has non-trivial solution linked to columns of A equal to columns of A being linear independent. And then we see from the previous theorems we can get a similar result by combining the theorem 1.5.2 and the theorem 3.3.1, because we say that case when A is squared we have a non-trivial solution if only if non-singular. And then here we have non-singular if only if the column is independent. Okay, and also we have something extra that we can do when it's a square matrix. That is, when it's a square matrix, we can calculate the determinant where it equals to 0. That will determine whether it's non-singular. And yeah, so basically I guess both the singular and the determinant, whether it's singular and whether the determinant equals 0. Those two properties are only defined for square matrix for us, and yeah. So before we can go to those middle steps, but here we have no middle step because our A is not necessarily a square matrix. Okay, and yeah. So that's for the solution to the homogeneous equation. Then we have the actual theorem here. That's 3.6.3. That says about the solution set to the general equation Ax equal to b. And it's very similar to corollary 1.5.3. So remember in chapter 1, we also had this 1.5.2 that characterizes A. By considering a homogeneous equation, then we have a corollary that's for the general equation. And anyway, so this theorem will have two parts. So first we say we characterize it for the first we characterize for the consistency. So that's I think it's the 3.6.1 we have. Wait, which one it is? Okay, sorry, it's 3.6.2, right? So this is the trivial. The first one part is pretty trivial. Theorem, and it says that if every b is if it's consistent for every b, then the column space will span R. So this is pretty obvious. So every b is inside the span of your column. So column space span the whole space, and and then we have this characterization that actually uses studying about the homogeneous equation, and it says that Ax equals b is only one solution, at most one solution, and if only if the vectors of A are linear independent. Okay, so it's a generalization of this thing, and here we are saying it's linear independent if only if X equals to only have one solution, and then we say when X equals to b for general b, then sometimes it has no solution, but we are basically ruling out the infinite solution possibility, and that's when the columns of A are linearly independent. Okay, so yeah, and I think the book actually has a proof over here of this, but here we skip the proof. And anyway, the proof is very similar to how you go from 1.5.2 to 1.5.3. So I guess it can be left as an exercise for you. And then from here we have so it's a really long discussion about column space. Anyway, then together we can yeah. Then together, then we have this description about column space that says if Okay, so if your column vector is a basis for n, and so both of these things should happen. So if you span Rn, then so what do we have here? Okay, so anyway, it's an easier thing. So we have yeah. So it's span Rn, then n bigger than n, and if it's linear independent, then n less than n. So yeah, it's pretty easy to check that if column is a basis of Rn, then so basically if the column is a basis of Rn, then then Rm is n-dimensional, right? Because you have n vector that's a basis for Rm. So but you know the number vector must equal to the dimension. So we know the dimension of Rm is n, so n equal to n. Okay. So it has a n vector basis, so the dimension must be n, and Rm also know dimension is n, so n equal to n. So it's just here. And also we have a small corollary we have here says that we have a small corollary here says that if A equal B has a solution for every B, then columns is a basis. Okay, and obviously that also means n equal to n. And here this thing we basically discussed before. So if it is n by n, if we have an n by n matrix, then it goes back to all the discussion here. Yeah, so if it's n by n matrix, then we can characterize all those things by seeing whether they are singular. And I think it's a little more. Anyway, n by n matrix is non-singular. Okay, so let's go this carefully. N by n matrix is non-singular if only if the columns form a basis. Okay. So yeah, so here we use theorem. So similarly we use theorem 3.3.1. Okay. So if they form a basis, so wait, a little confused. Okay, so the proof has two directions. So first direction is if they are basis, then the vectors are Li, and by 3.3.1, then the matrix is non-singular. And now I'm confusing myself a little bit. And if it's non-singular, then we know the vectors are AOI. And okay, now I remember. Okay, and okay, so the vectors are non-singular. Then so the other direction is the matrix is non-singular. Then the vectors are AOI, but it's n vector in n AOI vectors in Rn. And then we use the equation, the theorem in 3.4 when we talk about basis. So we have NLI vectors in Rn, then they form a basis. Okay. Yeah. So that's a proof. Okay. So that's a lot about column space. Oh, actually a little slow. Anyway. Then that's a lot about column space. Then we have this weird, a little weird organization that we go back to talk about row space. Okay. And but before then, remember we have the definition that about the null space. Okay. So remember we had this definition that null space of A is is a set of vectors in Rn that satisfy Ax equal to 0. Okay. That's a null space, and then we can define so when we define null space, we don't know what's dimension, but now we know dimension, so we can define a dimension of null space, and that's called nullity. Okay. So nullity is the dimension of null space. Okay. And then we have this rank nullity theorem that we call okay, that will describing a little weird lesson. But anyway, so this is actually about the row space of A, at least by the presentation here. Okay. Okay, so I think let's try to draw this better. Okay, so let's think about the rows of A, right? So A is n by n, right? Okay. Okay. So what I'm thinking is A is n by n, right? N by n, and so there are. So you think about the rows, there are n-dimensional vector, okay? So anyway, what we want to see is the rows are inside this Rn, right? Because they are n-dimensional vector. And so what this rank nullity theorem says is a very strong correlation of Rn, but well, more intuition will be more clear when we go to later chapter. But basically, we want this theorem is the result of a very strong correlation about this Rn. So actually, what we have is Rn equal to the row space of A, and plus, I'm not sure where I choose the right circle, so maybe. So this is something special that we haven't talked about. So this n-dimensional space is the row space of A plus the null space of A. Okay. This is what actually happened, although we haven't been very clear about this plus circle thing. So, okay. And but intuitively, it is an n-dimensional space, and you can separate it into two parts. So there is a row space part and a null space part. And actually, everything between them is orthogonal, although we haven't talked about orthogonal, so you only have a rough idea about this. But yeah, so this is a high-level idea of this theorem. It says this Rn can be separated into the row space part and the null space part. And so this n dimension equal to the dimension of the row space plus the dimension of the row space plus the dimension of the null space. Okay. So dimension of the row space is our rank, and the dimension of null space will become n minus r. So rank r, and the dimension of null space is n minus r. Okay. So that's the idea of this theorem. And okay. And we have this proof kind of by example, because I think it can be made rigorous, but it's just a lot of notation, not very interesting. So anyway, the idea of the proof is you do, so we are studying a row space, and the row space has a nice property that it doesn't change by the row operations. So we can do Gaussian elimination, and we go to, actually go to reduced row echelon form. Okay. So we turn A equal to its reduced row echelon form, and we call it U. Okay. And so here is example, we turn A equal to U, and we just, so those two things have the same row space, and we just count how many lead variable and free variable it has. And as before, we know the number of lead variable equal to the dimension of the row space, so it's 2 here. And also from the calculation before, so when we talk about null space, then we see that the null space is spanned by the vectors that same number of vectors as the number of free variables. Okay. And yeah, so we can do the calculation here, and we see that each free variable lead to a vector that's some vector inside the null space. And okay, and so those vectors, it's easy to see that they are linear independent, because so on the coordinates that correspond to free variables, say the first vector is correspond to the second variable, so it has a 1 here, and all other vectors will have a 0 here. And similarly, the fourth variable corresponds to the second vector, so it has a 1 here and 0 here. So they are linear independent. And also, so we don't say it's a basis for n of A, and this this we actually argued before, although we didn't do very carefully. But basically, what we say is we have solved this, and we're seeing that we have a most general solution here because you put arbitrary x1, x2, x3, x4, then these two coordinates we have been set as free, and the other two coordinates are already totally determined by those two equations, and so those are already the most general solution you can have for the null space vector. So we say this span the null space, and so yeah, so those two vectors, they are basis for null space. So so that means the dimension of null space is 2, and so this is not very general solution. So if you write this in whole, you might get point deducted. But anyway, we are being a little lazy here, and hopefully you can generalize these to more general cases. Okay. Yeah. So that's for rank nullity theorem question. Yeah. So we have a proof by example, not very rigorous, but yeah, writing out everything is a bit annoying. So hopefully people buy this. Yeah. And anyway, so finally we go to our last theorem. It's about our rank. And so first we go to something about column space and the row operations. And so once again, we're thinking about between A and U. Okay. So as we said, the row operation doesn't change the row space. So you can go from A to the row echelon form and A and U. I think it's also reduced row echelon form. Okay. It's better. Okay, so it's also reduced here. So we go from A to the reduced row echelon form. Reduced row echelon form, and they have the same row space. And what about the column space? They have different column space. Okay? So that's a little unfortunate, but what's good about it is that they have the column vector has the same dependency relation. And that means x equals 0 if only if ux equals 0. And so what do we mean by same dependency equation? It might be clear if we see an example. So we have A and reduced row echelon form of A equal to this, okay? And so they have the same row space, and they have different column space because the columns has a non-zero entry here and the column has a 0 entry here. Yeah. Yeah. And so you see the column space are different, but we say they have the same dependency equation. That means how you, so if some linear combination of the columns of A equals 0, then the same linear combination of the columns of U will also equal 0. So a very good example is these two, right? So you see, so maybe I like this way better. So we have the A1 vector, 2A1 vector minus A2 vector equal to 0, right? So you have twice this vector minus this vector equals 0. And then you have the same equation. So 2 of u1 minus u2 equal to 0. And we think about this, that's the equation when you solve for, so this is saying AC equal to 2 minus 1, 0, 0 is the equation, is the solution for this. And also x equal to 2 minus 1, 0, 0. And so those two are saying x equal to 2 minus 1, 0, 0 is a solution for both of these. Okay. Yeah. So even though the column space is different, the column space has a certain dependency equation. So same solution, so same linear combination of them with will go to 0. Okay. And from here, okay, 10 minutes. From here, then finally we can prove the theorem that we have been saying that's true. That's rank also equal to the dimension of the column space of A. Okay, so n by n matrix, then the dimension of row space. So this is a rank. So dimension of row space, as we say, it's a rank, and so the rank of A equal to the dimension of the column space. Okay. And so the proof has 2 steps, and that is first step. We are going to prove the dimension of the column space is actually greater or equal to. Okay, so here is a little funny. First, we want to say the dimension of column space is bigger than the rank of it, is bigger than the dimension of the row space. So here we actually want to say this is the dimension of A. And from here, then we can prove that the dimensions are equal. Okay, so let's see the first step. The first step is harder. Okay, and actually, okay, so there are a lot of there are a lot of matrix here. Okay, so maybe so I want to erase this. So yeah, okay, so this is actually annoying. I should move it wrong, but anyway, so let's draw the matrices. So there is the A, okay, and there's the reduced rational form of A. That's the U, okay, and so we do something very funny. So U is like so U is a reduced rational form, right? Let's see, do we have example? Okay, so maybe let's do this example. No. Okay, so we have A and we have the reduced rational form. Okay, A like this and U like this. And so it's like this, and so once again we are counting the lead variable and the free variable. Okay, so U has a lead variable here. Okay, and what is funny is then we will pick out those 3 columns. Okay, okay, and so we'll form a UL that equal to 3 by 4 matrix. Okay, and also then we'll pick out the same 3 columns. Okay, and we'll form a AL equal to this 3 by 4. Just slow. Okay, and so we have a E and a U, and we have AL and UL. Okay. So AL and UL are smaller, and A and U are very long. Okay, so that's UL. That's a matrix obtained by from U to only the lead variable of U, and A is you pick out the same columns. Okay, and so we know that AL and UL are row equivalent because yeah, it's easy to check. So because the deleting columns doesn't change the row equivalence, is you can still go from AL to UL by the same row operation. And then we have the columns of U are linearly independent, and it's a pretty okay. So it's a row rational form, but not reduced row rational form. But the columns of U are linearly independent. It's pretty easy to see because it's actually reduced rational form. Then you will be like 0 here, right? You will be 0 here, 0 here, and so you see that the columns are linearly independent. Okay. And then so columns of UL are linearly independent, and so the columns of A will also be linearly independent, just because of the thing we already said. Okay? Because they have the same dependency on the columns. Okay, So between UL and AL, the columns are all linearly independent. Okay. And okay. And let's see what we have. And AL has rank A linear independent columns. Okay, so it's really long. So this thing is a lot of calculation. Okay, so then we go. So the non-zero rows of U. Okay, so then we go from. So we have a really long chain of equation. So here we have the rank of A. Oh, where am I? Rank of A equal to the number of non-zero rows of U, and that equal to so non-zero rows of U equal to the number of columns of UL, because that's how you form. So you count the lead variable here. That's okay, equal to number of lead variables, and equal to number of columns in UL, and and that also equal to number of columns of A, right? Of A, L, and then we know the columns of AL are linear independent. So and so from there, okay, so we need longer. So rank of A equal to, so the number of columns of AL and equal to number of columns of AL equal to dimension of column space of AL, because they are all linear independent. So the number is a dimension. Okay. Okay. So from this really long equation, really long chain of we have this really long chain of equivalence, and we see the rank of A equal to the dimension of the column space of A. And okay, and then finally we can get to our greater equal to, because AL is formed by deleting columns of A, and so this thing must be smaller equal to the dimension of column space of the original A, because you are adding vectors, the dimension cannot get smaller. Okay, so we're over time, we're too slow, but I guess it's okay because our schedule is quite okay. But anyway, so yeah, so with really strong equation, then we get this dimension of yeah. Finally, we get rank is smaller equal to dimension of column space of A. Okay. So we go all the way through this chain, and we back to two things about A. We have the rank is smaller, so the rank, which is the dimension of the row space, is smaller equal to dimension of the column space. Okay. So we have this here. And yeah, then finally we actually, oh sorry, we're over time a little bit, but let me finish. And then the second part of proof is you use the symmetry between row and column. So you do the same thing. Then we see we consider the transpose of A here. Okay. So if you think about this same equation to the transpose of A, then the column space and the row space will swap each other. Okay. So here the only thing is you consider this A of T. Okay. And yeah, so the column space of AT is the row space of A, and the row space of AT is the column space of A. So you can get the same equation, but just swapping the equal sign direction. So you have the row space of A, dimension of row space A is greater equal to is greater equal to the dimension of column space of A. And yeah, so finally we proved our theorem. The dimension of the row space equal to the dimension of the column space. Okay, any question? Sorry about overtime, and we have some additional slide here, but actually not quite in the book, but yeah, yes. Maybe you can. We can finish it later, but anyway, we'll have homework about chapter 3 today, and yeah, if no question, let's see you on Monday. Okay. Yeah. Sorry about overtime.